dot, 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 dot to sync my audio. Okay. So we're going to continue exactly where we picked off in class and on to example 6 of the first part of 3.5, which is the midline of a sine function. So we're going to do it graphically first and then using an equation. So this time we'll start with example 6a. Right? Midline is just going to be like the physical midpoint between our maximum and minimum values. Right? So in this case, if our maximum is 5 and our minimum is this -1, our midpoint is going to be that point directly in the middle, which is 2. So that's y equals 2. And I mean, that's it. That's the answer for that. And it says sketch the equation of the line in red, which I did. Alright, so now moving on to B, right? You just have to be careful with your scale. Looks like this point's 2. This point is -8. So that's that difference of 10 there. So our amplitude's 5. It's always just good habit to also figure out the amplitude. So it looks like our midpoint here with is -3. So y equals -3. Alright, so that's graphically. But now imagine we don't have our graph and now we need to use an equation. So beforehand we were using this value here and this value here. But now we're going to just look at like the transformation of the function vertically. So in this case, this little -5 off to the side, that tells us what our midline is. So in this case, since it's a -5, this is going to be y equals -5. Since we're shifting our main function down by 5 units, our midline is now y equals -5. So we're translating down 5. So for example B, if it says +4 at the end, instead of going down like the last time, we're going up. So our midline is going to be y equals 4. And that's just because we are translating up by 4 units. Okay, and I'll move on. Now we're on to lesson 5b. So we've talked about period before. We know that it's 2 pi over b, with b being the number, excuse me, b being the number that's multiplied on the inside of the parentheses. So I'm just underlining kind of like where I'm talking about. But then there's also something called frequency, which I do believe we've touched on a little bit, but not super recently. Right? Frequency is the number of complete cycles in the periodic curve that the periodic curve completes in a unit interval. Sorry, guys. Which is, instead of 2 pi over b like the period, it's b over 2 pi. So we're going to have to be careful not to mix that up. And then also just as a little note, like period is going to be like for pure units, time over cycle. And frequency is the cycle over time. Just like directly in terms of what we're talking about. Alright, so now we're going to use the equation to find the period and the frequency of each function. So period, right, is our 2 pi over b, which is going to be 2 pi, and our b value is this 1/4 here, so 2 pi divided by 1/4. We're going to have to do our flipping of fractions here, and 2 pi divided by 1/4 is the same thing as 2 pi times 4. So that's 8 pi is our period. And then our frequency is now going to be b over 2 pi, which is 1/4 divided by 2 pi, which is going to be 1/8 pi. So see, they just kind of flip-flop there. Okay, and now on to example B, right? We have 2 pi over b for the period. And it looks like our b value is 48 pi. Usually we don't see a pi in there. So we have 2 pi over 48 pi. So our pi's actually cancel out for once. So we're going to get 1 over 24 as our period. And then frequency, pi over 2b. We're going to get 48 pi over 2 pi, which is 24. So see how we're really just flipping the fraction here? 1 over 24 to 24. And our last problem, 8 pi to 1 over 8 pi. Because that's effectively the only difference between the formulas. Alright, so now we're on to a more of a free response type question. Example 9. It's saying a mass on a spring oscillates back and forth and completes one cycle in 0.25 seconds. Its maximum displacement is 6 centimeters. Write an equation that models this motion of if the spring is released from the maximum height. And then also find the frequency. So we are being asked for quite a couple things here. We need to figure out what it's given us. So it says it completes one cycle in 0.25 seconds. Alright, and then maximum displacement is 6 centimeters, and then write an equation that models this motion if the spring is released from the maximum height. We have to recall, like, when this is going to be a sine or a cosine equation. And since it's being released from a maximum, thinking back to our key points of sine and cosine functions, this is going to have to be a cosine. Since cosine starts from a max and then dips down and ends in a max. So that's why I'm picking cosine here. Alright, and then it's also just asking us to find the frequency. So let's pick a different color. So finding the frequency. Alright. Oh wait, I also didn't even point out what is 6 centimeters? 6 centimeters maximum displacement. That's going to be our amplitude. So 6 centimeters here. So we're going to have D equals, I'm going to put 6 instead of A, cosine of B T. We don't know B yet, we don't know T yet. But we are given our period. It says it completes a cycle in 0.25 seconds. So 2 pi over B is equal to 0.25. So we're going to have to solve for B here. If you change this into fraction again, this would assume that we're not having a calculator here. So if we end up doing our cross multiplication here, we're going to have 8 pi is equal to B. So we can fill that in now off to the left. So D is equal to 6 cosine. And we have 8 pi T. Technically this is in centimeters. Alright, so that's our equation. And then we need to figure out the frequency. So frequency is B over 2 pi. Or you can just look at what our period is and inverse it. So our period is 0.25 or 1 over 4. So that means our frequency is going to have to be 4. But I'll also solve it the math way because we found out that B is 8 pi. So 8 pi over 2 pi is equal to 4. And then in units, that's 4 cycles per second. Whereas the period is displaying 1 cycle's time length. Okay, now on to example number 10. We have 3 different questions here, but all asking the same thing. So we're going to consider our graphs given below, and we are going to find our 5 key points for one period. By key points, we're talking like maxima, minimum, intercept, things like that. We're going to identify where the function's concave up or concave down. We're going to identify the intervals where the function is increasing or decreasing. And then we're also going to name our points of inflection. So remember, at the top here, our point of inflection occurs where a graph changes concavity. And then it also adds this new sentence here. It occurs on the midline. So using this little paragraph above and just our previous knowledge, let's go ahead and do example A. So find their 5 key points for one period, just one period. So it's looking like just, I'm sorry guys. This graph, it starts at an intercept. So this is a sine graph here. So our key point, I'm gonna do it in green. We have one there, 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 and there, and it ends at an intercept. And I'm stopping here, even though it shows us more, because this is just one period. This is the length of one full cycle. So it looks like our full cycle is from 0 to 2 pi over 3. All right. Which means that our period is 2 pi over 3, right? So our period is equal to 2 pi over 3. Okay, cool. So part A is going to be just listing off the coordinates, right, that we just drew. So we have 0, 0. We have over, let's see, pi over 6, up 3. All right, we have over pi over 3, up 0. We've got pi over 2 minus 3. And then we've got 2 pi over 3, 0. These are all of our points. Also, our amplitude is just going to be displayed here, right? Our midline is just the y equals 0. And then our amplitude is going to be 3 here. Just some other things to add. All right, so now we're going to identify where the function's concave up and concave down. So in this case, we're only going to have 2 intervals, right? Because from this first point here where it starts out to pi over 3, well, let me use a highlighter because I'm pointing, but you can't see that I'm pointing. This interval here is concave down, right? Because it's a frown. And then the interval afterwards is concave up. All right, so part B. So our concave up interval is going to be from pi over 3 to 2 pi over 3. And then concave down is going to be from 0 to pi over 3. You can write concave down first or concave up first. I don't know. It feels right to say concave up first as opposed to concave down. So the order of which you write this is fine. But of course not the intervals. Intervals, you're always working from the smallest number to the largest. All right, so now let's take part C. Identify the intervals where the function is increasing or decreasing. All right, so increasing, that's just physically where the values of our function are just going up. This is not really indicative positive or negative. It's just like, where are they starting to go up? Let's see if I can get a different color. Okay, I'll use a screen here. So where we're going up on our graph, I'm going to start to highlight. So there's that first point there, right? From 0 to pi over 6, our graph is definitely going upwards. But then from pi over 6 all the way to pi over 2, we're just going down. But then pi over 2 all the way up to 2 pi over 3 is where we're going back up again. For just the cycle of this function, right? Technically it does go up further, but we're ignoring that. All right. So then, of course, anything I didn't highlight is where we're going down. All right, so part C, we have intervals of increasing from 0 to pi over 6. And pi over 2 to not add link. What the heck? What the heck is that? Okay. Y'all. All right. We're just going to leave. We're leaving it there. Actually, no, let's just undo it like that. Okay. Moving on. We have pi over 2 to 2 pi over 3 for that. And then our decreasing intervals, well, just interval in this case, is from pi over 6 to pi over 2. Awesome. And then finally, our points of inflection. So our points of inflection is where our graph changes concavity. So we can look at our point B for reference, but they also told us that it lies on our midline. So that's really helpful for that. So there's 2 points here. Right, we have pi over 3 and we have 2 pi over 3. So these two for our points of inflection. Wait, I just need to use a different color. Right, our points of inflection are going to be x equals pi over 3 and then 2 pi over 3. I will say, so technically you're probably thinking like, well, what about x equals 0? Because the graph just kind of starts there, we're not counting that one since that's just where it starts. So it's not actually changing concavity since it's just starting out already as concave down there. But then with pi over 3, it's switching from concave down to concave up. And with 2 pi over 3, it'll be switching from concave up to down eventually in our cycle, since it doesn't extend anywhere. Like as in visually here. You'll note, I'm just going to scroll down a little bit. So notice how in example A, I'm just going to draw with my highlighter. Our little sine graph does not go down again past our origin. So that's why we're not including that point as a point of inflection, because it's not actually changing anything. But then if you look down at B and C, with C, we are going to call out this point as a point of inflection, even though it's just like a different cycle of the same function. And that's because our function is continuing in that direction. Hopefully that makes sense. If not, you can always ask for clarification later. But all right, I am not going to personally go through examples B and C, but I will quickly put the answers on the screen in just a second so you can see if you're right. But I would like you guys to make sure you can do these. All right, so here is example 10B. Right here. I'll leave it up for a second. And then we have example 10C. So 10C is a little bit different because, like, not in terms of how you solve the problem necessarily, but visually, this is a sine graph because it starts at an intercept, but it's going down. So this one will actually have a negative sign in front of it. Not a requirement of the problem, but definitely good to know. Oh, and also if anyone's wondering how I got like this 3 pi over 4 and this 9 pi over 4 here, this is just by figuring out this kind of midpoint here between pi over 2 and pi is going to be our 3 pi over 4. All right. now on to example 11. So we definitely have an FRQ type question here. It says a buoy oscillates as waves go past. For any given time, it moves a total of 4.5 feet from its low point to its high point, and then returns to a high point every 15 seconds. And notice we have our little calculator symbol up in the top. So this is a calculator problem, which is nice. We haven't used that in a while. Alright, so let's figure out what the heck they gave us. Alright, they give us a nice little visual. Alright, it says it moves a total of 4.5 feet from its low to its high point, and then returns every 15 seconds. So this returns to a high point every 15 seconds is making it sound like that's the period. Right? It returns every 15 seconds. So from like here to here, where I'm drawing, seems like that's 15 seconds. Because that's what they told us. So that's what we have to assume. Alright, and then there's this 4.5 feet from its low point to its high point. So all the way from the lowest to the highest is a number they're giving us. So they're not exactly giving us our amplitude though, because our amplitude would only be half of that, right? So they're saying like this entire thing total is 4.5. But our amplitude, again, is only half of that. All right, so let's just write our amplitude since we know that. So 4.5 divided by 2. All right. So what is that, 2.25? 2.25. You can also just keep it as a fraction. But with a fraction, we don't like to mix fractions and decimals, so you could call it 9/4 if you wanted to. But all right, so it's saying write an equation that models the motion of the buoy. So we're going to have to find amplitude, which we did. We're going to have to find our B value. And, I mean, yeah, that's all we got to find. So we already have our amplitude. And remember, it's... Oh, wait a second. I did not call out which function we need to use. It doesn't specify. Right? It doesn't say sine or cosine, so we're just going to have to use how this, the buoy moves to determine that. So if it's starting out at a high, that means we're going to use cosine. Right, so we have D equals A cosine B T. So let's plug in. So we have D equals, our amplitude we already found, 2.25. Cosine, we keep as cosine, but B, we need to find B. So B comes from our period formula, 2 pi over B. And if we know that our period is 15 seconds, that means we can work backwards there to find out what our B value is. So let me just do that here. I'm trying to think, just because we can use the calculator, which actually let me pull up my NumWorks calculator because I really don't want to start to work with a bunch of decimals, especially if we have pi here being all nice for us. So just give me a second. Because in order to solve for B, that's effectively, we're going to get 2 pi over 15. Is there a way I can simplify that? Not really, actually. It just turns into a decimal. Okay. So this starts to be on personal preference. I honestly strongly recommend you leave things in simplified fraction form just because that's what we're used to seeing, especially on the non-calculator forms. So basically what I just did here is solve for B. But whenever you solve for B, you're going to get 2 pi over 15. The thought process there is because, right, you have to cross multiply. Okay, we're going to have 15 times B to get rid of B. But in order to get B by itself now, here, I'm going to write it out instead of just talking. You have 15B, right? But then you need to divide both sides by 15. Right, so that's how we end up with B equals 2 pi over 15. I don't want to use a decimal. It's 0.4188 0.79, blah, blah, blah. Don't feel like using that. We're going to keep it in this simplified fraction form. So I'm going to move our function down here just so I have room. So you have 2.25 cosine of 2 pi over 15t, and it's specifically feet. All right, because we're given units here. We're given feet and we're given seconds. So that is our equation. All right, and then we're asked, what's the frequency? So frequency is going to be b over 2 pi, but it doesn't just ask for frequency. It also says explain what that means, which basically that's saying explain what your units are. So we know that our frequency is going to be 1 over 15. This isn't cycles per second. And I know that because our period is 15, so if you just flip the fraction of the period, we'll be given the frequency. So, like, what does that mean? 1 cycle every, or 1/15th cycle per second. It's just saying that the buoy is moving 1/15th of its path per second. So the buoy is moving 1/15th of its path per second. Because that's how far it can get in a second, basically. Alright. And then part C is we're going to be using our graphing calculators to find the point of inflection where the buoy is at equilibrium. Which equilibrium would be where it's changing from concave up to concave down. It does kind of call that out in this graph. It's not super clear because it does mention the word equilibrium, but matching the diagrams, right? That is this little green point that I'm trying to draw here, equilibrium. So that's going to be on the midpoint. So how you graph this is you are going to type in our function that we made in part A in your calculator, and then just look at it in the graphing function. So I'm going to do that now just to see if I can anticipate any weirdness that our graphing calculators like to give us. 2.25, we have cosine of 2 pi over 15. Don't forget your parentheses, okay? Not a horizontal line, see? I'm glad we do this. Oh, don't forget your variable like I did, right? So I actually just forgot to type in my t, right there. So don't forget to type in your variable here. And remember, you don't have to type in the letter t, just type in x. All right, and then once that happens, you're going to get a nice cosine graph. That is going to start out at a max, right? It's going to look like that on your calculator. Just to know that you're doing it right, I guess, this point that it starts out at is going to be y equals 2.25, okay? Alright, so at equilibrium is where it changes concavity, which is our point of inflection, which is our midpoint. So that's going to be along the axis here, along the x-axis. So if you move your arrow over to the right a little bit to find a 0, you're going to get an x value of 3.75. And this is 3.75 seconds. So the buoy reaches equilibrium at 3.75 seconds. And that's because the path is changing from concave up 2 down. All right. All right, and then it says, what does equilibrium of the buoy mean in respect to the behavior of our waves? We kind of already talked about it in this example, but the behavior of the waves at the equilibrium point is just like the height. Basically, it's the midline. Right? It's at the midline of the height of a wave. So midline of height of a wave. All right, and then identify intervals where the buoy is decreasing. So based off of your calculator, you're gonna just look at your graph and see where we are decreasing. All right, sorry, the height of the buoy is going to decrease from maximum to a minimum point because this is our cosine graph. Sorry. And it's just, I'm just going to say the answer here. It's going to be from 7.5 seconds all the way to 15 seconds. But then also because these are waves and we're just going to assume that they're indefinite, it's also going to occur every 15 seconds afterwards. Right? So like every time there's a decrease, we're going to have, you know, like our little increase that's happening. Oops, I didn't mean to go that far. And then we're going to have our decrease again, and this is going to happen every 15 seconds just because of the period. Right? Because one period is 15 seconds. So after every 15 seconds, we're going to start to decrease again. So from 7.5 to 15. So then I think the next value would be like, we're adding 15 seconds to 7.5. It'd be like 22.5. Yeah, basically this and every 15 seconds after. Okay. So that's it for 3.5. Make sure you do your homework and circle any questions that you have for me for when I come back.